We will just wait for 1 minute for everyone to join who wants to join, and then we will immediately jump into the topic. People keep coming. Yeah, we already have 30 participants at this stage. Okay, so I guess that people will keep going online, but since we want to start on time and we have our presenter for today here, I would say that we can start, and I will start sharing my screen to introduce the topic of today. Give me 1 second. Okay. I guess that you can see my screen now. Arne, can you confirm?
Yes, I can see it.
Okay, great. Yes, welcome everyone to this best practice webinar organized by the Renewables Grid Initiative. It is a webinar that will be on the topic of smart forecasting for resilient grids. And before we jump into the content, I would like to give you an overview of what we are going to talk about today, and also just very briefly a bit of housekeeping. So this webinar is recorded and will also appear on the RGI website and on the RGI YouTube channel, which is important for you to know beforehand, in case you do not like. After setting the scene, I will pass the floor immediately to Arne, who will talk about the methodology framework for near real-time probabilistic risk analysis for digital forecasting and planning. And after, we will have a Q&A session, an extensive Q&A sessions where all of you will be able to ask your questions and to interact with Arne. I think Arne will be very happy about discussing all the details together with you. And we will have a short wrap up at the very end of the webinar. But before, I would like to very briefly introduce you to the Renewables Grid Initiative. Many of you who are online with us today might already know us, which is great. But just for those that are with us for the first time, I would like to show you who we are. So RGI is a unique collaboration of NGOs and transmission system operators from across Europe. As you can see, we cover most of the European countries, and in most of them we have both representatives of TSOs and NGOs. And we work on 3 different dimensions that you can see on the screen. We have a team that is working on grids and electricity and energy systems. They are looking into modeling, planning, and implementation of the decarbonized and optimized energy system. Then we have a team that is working on energy and nature, ensuring that energy systems are built in coherence with nature and biodiversity. And we have an energy and society team that, of course, looks at the engagement with citizens, with civil society, and with policymakers. We are trying to combine everything into one and to look at all the aspects in our work and in each topic that we talk about, which is very important.
Okay. Yes. So I'll just do a short introduction here. So first of all,
Arne, sorry, I'm back.
Okay.
It seems that we are having some issues here at the office. So I would just say that you start now, and we can do the rest afterwards.
Yeah, sounds
Yeah,
good.
just to not have the risk of losing me again.
Yeah, I'll do that. And maybe we can you can take your kind of introduction of RGI at the end, maybe with the...
Exactly. We can do that. We can be flexible.
Yeah, okay, perfect. Then I'll start my presentation. So first I want to thank RGI, and we are honored to participate and play a part in RGI's important work. And it was a very nice experience participating on the 6th PCI Energy Days, where we received the award. And I think the stage was set there by a lot of top politicians in the energy space for addressing what is needed in the coming decades and what they're planning to do. So that was very good. So let me see. So first I want just to say thank you, PCI and RGI, for the award that we received. And I think the jury's reason for giving the awards was very good. And maybe Mara can play that at the end if the technicality is resolved. So I just want to, since we were not able to have a thank you speech on the award, so I would like to have a small thank you speech first. So I just want to say we're truly honored to receive this award at the 6th PCI Energy Days. And this recognition is not just for our work, it's a call to action. So since Europe is facing a gridlock, in the short term, the only viable solution is to use our existing power system closer to its limits, safely and intelligently. And all other options are either too slow or too costly. So to keep businesses thriving and society powered, we must quantify risk, manage it cost efficiently, and coordinate across company and nation. And I also want to say a special thanks to Tørris Digernes, whose vision and mathematical foundation made our predictive risk assessment methodology possible. And by blending Markov models, Kronig product, and smart aggregation, Tørris created the basis for what me and my team have developed, a framework for near real-time probabilistic risk analysis of large power systems, a tool that Europe urgently needs now. I also would like to acknowledge the late Jan-Ove Gjerde, former head of R&D at Statnett, whose vision laid an important foundation for the work we continue today. So, why the RG award is important? So, from LinkedIn this week, Dan Jørgensen, the EU Commissioner, had a couple of very good and important posts. So, yesterday, Europe ends its dependency on Russian energy and accelerate a secure and clean independent energy future. A couple of days ago, Europe advances 235 strategic infrastructure projects to drive integration, decarbonization and security. And earlier this week, Europe cannot deliver clean, affordable or secure energy without a fully interconnected and modernized grid. So, insufficient grid capacity leads to higher cost and a waste of renewable potential, while stronger cross-border network could generate major economical and social benefits. So investing in grids means investing in Europe's future, enabling renewable energy to flow across the continent. And this is a quote from Dan Jørgensen the last week. And I think it set the stage very good for what's on the political agenda, energy agenda. And just to summarize there, what Dan Jørgensen was asked, why he's obsessed with power grids. So as he said, Europe's energy infrastructure is not just the backbone of its energy system, it's the backbone of Europe itself. And he highlights that investing in grid reinforcement and cross-border capacity could unlock massive social economic benefits, from billions in annual savings to stronger market integration and GDP growth. And so as investing in grid means investing in Europe's future. And as he said, enabling the wind from the north and the sun from the south to power the entire continent with clean, affordable and secure energy. So to segue Dan Jørgensen's comments on LinkedIn this week to what I'm going to present today is how to get more of the existing road and how to build bridges while managing the risk that follows. So the story I'm going to tell today is divided into 5 parts. I will first have a short introduction addressing important changes that has happened the last couple of years and why this matters today. Part 1, setting the stage and explaining how we can quantify risk and defining the problem around this. Part 2, asking the right question and trying to answer it. Part 3, go into 3 specific use cases that will contribute to open the gridlock. And finally, a conclusion and a summary. So part 1, introduction, addressing important change. I will just go into a short timeline from where we started our development with the mathematical framework project and R&D that has been made, and finalizing getting over to the regulation change from Asia the last couple of years. So in 2002 at the university in Trondheim, I did my master thesis, and during this master thesis my guidance, Tørris Digernes, discovered a solution to the Markov model that was published in this master thesis that kind of opened this possibility space that we are presenting today. This was later included in an international textbook on the subject by Marvin Rausan in 2004. Was included there, and a new chapter was added, Markov models for complex systems. And in 2009, Statnett, the national TSO, came to us and asked if our new methodology would be able to do this kind of probabilistic risk calculation in system operation. And their need was that they wanted system operation to assess the risk equally and do the right or the same risk measures evaluation for all the people on that shift. And the scope was in real time and for the coming shift. So that's where it started at Statnett in Norway. The prototype ProMaps Online was up and running in 2013, so we got to test this on the Norwegian power system over almost 2 years then, and where we got the insight of how this probabilistic risk and security of supply quantification give us a new insight. And this has been tested by several large DSOs and international TSOs as well. And another important moment in time here was the GARP project that went for, I think it was 4 years, 3 or 4 years, and was completed in 2017, where they focused on reliability principle and uncertainty for modeling probabilistic risk in power system. I founded ProMaps Technology 2017. 2019 was an important date where the CSAM regulation change was published. I'll come into what they mean. I just want to have the timeline here. And also the 70% capacity rules from Asia 2019 for the interconnectors in Europe. So to the 2 rules, the 70% capacity rules will be in full effect at the end of 2025. And the CSAM coordinated security analysis methodology by 2027. So just to highlight this, the CSAM rule provides the necessary tool and procedures for TSO to address the rated higher level of capacity on the interconnectors, and thereby supporting the objective of the 70% capacity rules that is coming in full operation in 2025. So by implementing the CSAM and following the 70 capacity rule, EU aims to achieve a more resilient and efficient electricity market. capable for integrating renewable energy sources and meeting future energy needs. So, in short, the 70% capacity rule forces TSO to load their interconnector more, forces the TSO to take a higher risk. The CSAM rule gives TSO a probabilistic framework in how to mitigate the increased risk. So, a lot of development has been done for many years and tested, and we have two now important points in time that both forces a change in our system, how we operate and develop it, and how to help the system handle the change. Okay, so part one, setting the stage, quantifying risk and defining the problem. So, let me see here. So just the title here, quantifying risk and security of supply in power system, the missing key for a safe green transition. So the power system, the foundation of modern society, it's often referred to as the world's largest machine, and must work in perfect balance where all participants play in harmony for the system to work. And production of goods, services, payment, all our communication, our hospital, our defense, everything depends on stable and reliability of the power system. So when the light goes out, society stops. Large power outages affect more than just light and heat. They paralyze our entire society. In a matter of seconds, everyday life can be turned upside down and our dependence on stable power supply becomes clear. So a robust energy system is not only important, it's vital. Blackouts in Europe, recent years. So in June 2024, several 400 kV power lines failed, leading to extensive blackout in Albania, Montenegro, Bosnia and Herzegovina, Croatia. April 2025, up to 60% of power consumption dropped out of in seconds. The incident had a major impact on parts of Spain and Portugal. And the power outage in Spain and Portugal affected millions of people, and we saw in the news a society that stopped functioning. The incidents show how vulnerable the power system is and how big the consequences can be. And the socio-economic costs are estimated to be between 1 and 4.5 billion euros. So, to the power system in general, all power system, all TSO, DSO has a main task and have a main objective. The task we all know, and also the objective, but I will focus on the objective. So that is to deliver demanded energy with as high security of supply as possible at as low cost as possible over the entire period. So basically, society is used to a high security of supply, and that the nature of that is into the design criteria that I'll come back to. So, did you know that our safety design criteria N-1 for the power system has remained unchanged since the 50s, and that it lacks the necessary transparency and flexibility, and it ignores the cost benefit. And although it has been very successful in providing a high level of security of supply to society, it has been having a high spare capacity that is not being used. Recently, I saw the World Energy Outlook 2025 from IEA. So, electricity use is expected to grow at least 2.5 times faster than the overall energy demand by 2035. System flexibility must keep up to ensure reliable supplies. Grid spending has risen at half the pace as new production. To reinforce electricity security, we need to have a sufficient dispatchable power and need to boost infrastructure resilience. So that's from the EER World Energy Outlook. And to look at this from a slightly different point of view, the change and the time problem we are facing. So electrification increases the load rapidly in a few years. Production changes and moves, even in few years. The power system needs about maybe a decade to build new capacity. So we have basically a problem with our system, which result in gridlocks, bottlenecks, and also increased risk for major outages. So we are entering a new system state. From a normal state we have had from the 1950s until now, with the N-1 security criteria, we are entering a new situation where the new normal situation is an abnormal situation. Before we come to a new steady state in the future, that may be N-1 or it will be maybe N-X. Anyway, the period we are entering or are already in give us more volatile energy prices, higher probability of blackouts, disruption and large-scale blackouts. So we have a system problem, basically. The power system is being pushed outside the design criteria N-1, whether we want it or not. And it's not possible to invest our way out of this fast enough to maintain the current safety criteria, at least not for the coming decade. So what we need to do is increase visibility, openness and flexibility. And by using new analytics, understand the current and future risk in the power system and thus optimize system operation and investment based on the best risk reducing measures. Did you know if we used a probabilistic safety criteria N-X for a power system, we could get full transparency, more flexibility and quantified cost benefit? And that we can use this today for our existing power grid and remove a large part of the grid limitation, which give the power system the time it needs to adapt and still provide society with a high level of security of supply. Okay, over to part 2, asking the right question and answering it. How can we calculate risk probabilistically in large, complex national power system? Why haven't this been done before? And if we can do it, how can we use this insight? I'll go over to the dimension problem. If we are thinking about Markov models, for example, several techniques you can use, but all have some kind of limitation. Just imagine a small power system with 60 branches. Each branch consists of 5 components, primary or secondary, for example. Each component can have 2 states. Functioning, failure state, for example. Just the state space of this probability will then increase or reach 2 up in 300, which is more than the number of atoms in the universe. So number of state increases exponentially, and that is a big problem. This can be solved with smart aggregation and other techniques. But what we need a mathematical framework that can calculate the probability function state for the power system, including all primary and secondary components. And also be able to model large power system. And the calculation also needs to be fast. So our work is based on Andrei Markov and Leopold Kronecker and built on stochastic processes and tensor and matrix algebra. And the breakthrough came with combining probabilistic models with structural algebraic operation to gain a new mathematical insight. And the first step was done in the my master thesis. But this pattern to synthesize existing mathematical framework to create new theories is what drives progress in mathematics and physics. And our work followed the same tradition with combining Markov and Kronecker on a new way. I'll not go into the mathematics, but just so you have a kind of brief sense of what we are doing here. So just imagine two components in a system, one primary and one secondary. Just imagine they have two states, functioning failure state. So we want to do the calculation on each of the component, getting the result for each of the component, but we also want to combine the combined state space in a total model. And this was mathematical proof was done in my master thesis, later included in the textbook. I'll not go into it, but this is kind of where it starts. Just a principle sketch on how to solve this for the whole power system. You need a reliability analysis. You have to combine it with flow calculation and combine this into a consequence model where you want the expected not supplied energy to be calculated and also the economical effect for not delivered energy. In addition to that, you need also a lazy load flow that is for a large part of the contingency and also the stability. So you can basically, some of the contingency you would experience will also create stability problem where the consequence of a contingency will be much higher. So combining all of these techniques into one framework, you're able to get a huge part of the property of the system inside this calculation. Just to visualize this, so just imagine here you see the complete Norwegian power system represented in an abstract three-dimensional graph. And for each of those branches, all of the primary and secondary component with failure rates for all the component, including also asset management, component state data. For doing the reliability analysis of the power system. And this is I like to call it the reliability on the power system. That's step one. Step two, we have to combine it with load flow calculation to get the reliability through the system. Basically the load delivery reliability. Then combine different contingency with stability calculation, so we can find which contingency that may cause a stability problem that may take out large parts of the system. Combining all that, I'll get into the result in the next slide, but basically for the whole system, have a graph showing how the risk in the system, total system, is changing based on how you're loading the system, the load flow, the breaker position, how much spinning reserve, how much flexibility is installed, what smart grid technology that is included, battery capacity, what have you. Everything will affect how the system will perform and how the risk will either increase or decrease. That sketch of that graph is the insight we are missing for having a more coordinated both system operation but also planning operation, not only for a TSO or DSO, but between TSO and TSO and between TSO, DSO and large consumer of power. So there is result visibility that is needed for understanding why the risk is changing on a system level. You also need very fast to understand what's the root cause of a given change in risk in your system. So what you need to have is the reliability result, probability of failure for each component, each branch, and the system as a whole. And then combining this with load flow calculation, have a detailed contingency list with all the contingency list inside a state space with a given probability that affect what contingency, single or double fault, that influence and the risk most in terms of risk, expected not supplied energy. And this has to be adjusted for stability sensitivity. So you want to basically have the contingency list, the risk graph, and a set of level that is acceptable or not for your system. That's a cost-use benefit analysis. And you want to have one look at the screen to understand if there is something you should do or not. And of course, the cascade failure that leads to big blackouts, you need to understand and have their own cascade contingency list. Here's where the stability analysis comes into play. So the insight we are missing, the key to better collaboration, how we open the gridlock. So risk is the combination of probability and the consequence. And risk over time with high resolution give us the insight that we need now. And to get a kind of a sense of this, the historical risk we can quantify exactly because the number of incidents we have registered, the amount of not supplied energy we have registered, so we have the history, what the result was. And doing this calculation in real time, that is based on failure statistic for each component type, each voltage level for all the components in the system, and the current loading of the system give us the risk now. That point on the graph is then should be in the same phase as historicals if there hasn't been a major change. And if you have that historical in real time, you have a good foundation to look ahead in time for the coming weeks, months and years. Of course, uncertainty will increase the longer you get out in a time frame, but you know your baseline is correct, and that is super important in today's world. When that is done, you have to quantify what is the acceptable risk level we can take and what is not acceptable. And this should be the trigger point for doing a risk reducing action where you use money to reduce risk before something happened. And this graph, I'll come to that, but that is the insight that everybody needs to have at the same time, so everybody sees the same picture if the root cause affect all. Okay, as I said, the mathematical part of the mathematical framework is already included in Magnus Raustad's textbook from 2004. Our development of the mathematics of software, what have you, has been included or presented in several international conferences. So just let me know if somebody interested in reading that. Yes, so this has been a kind of a long development with both learning as an engineer, the probabilistic approach by itself, the probabilistic approach applied to power system, applying that in combination with traditional power system analysis, and understanding what insight this gives us that is not there before. And the final step, doing what we did in scenario analysis in the start, in their real time, and being able to present huge system analysis fast in an aggregated way so system operation can understand it, but also opening kind of the silos inside a TSO, since that risk graph I just showed you is basically every department's goal, just a different time frame they are looking at. As I said, having as high security of supply as possible at as low cost as possible is everybody's goals inside a utility and also the top management. So that graph kind of represents something important in our utility. Okay, part 3, a precise use case and how they will contribute to open the gridlock. The technology is available from the real-time security assessment and also from ProOne's real-time probabilistic risk analysis of complex power system. Over to the use case, and this is the important thing, I think, having as good use cases as possible. So the first one, I just explained the operation and planning operation. I've touched on this during this presentation as well, but in system operation, you want the operational shift, the people at work in system operation, to assess the risk level they are facing right now the same way. Whether you have long experience and short experience, you assess the risk the same way. And also you will evaluate the risk mitigating action the same way as well. And this is connected to doing the right cost-benefit action. If this acquires spinning reserve, acquiring more flexibility, putting system operation in work, what have you, everybody should assess this the same way. And for system operation, is one look at the screen, is the risk level over a certain threshold, you should go into a study mode, test what action you should do to reduce the risk into an acceptable level. I can illustrate this with our actual outage in Norway many years ago, where we were up and running with this software. And we saw in real time how the risk was changing and how this led to a big outage. And it was back in 2014. The prototype was up and running in the R&D environment started at that time. And there was a major outage in the west coast of Norway. And the interesting thing here was to see the day before, the risk level for that area was in a normal state. Suddenly it increased by almost 50%. And it stayed high for 19 hours before there was a big outage. And this was due to a 420 kV power line and high wind that led to mechanical failure on one of the towers. And by seeing this, okay, so the risk increased. What was the reason for that? And in this case, there was a down regulation of production inside that area for importing production from the north that was cheaper. So that was the reason why it increased in the system. And for the total contingency list for the whole of Norway, the contingency that was #1 in that specific area was not on the top 100 list for the whole of Norway the day before. So you get kind of a sudden change on the contingency list that is affecting this when you are calibrating for the likelihood for happening and the consequence. So the interesting question here was, of course, what if we had more spinning reserve inside the area? Could this consequence of this failure be avoided? So we tested this and we calibrated how much spinning reserve could be made available inside the area and still import from the north what you wanted. And we tested this, and if you can't remember the number, but you had the right amount of spinning reserve with this outage, the system there would be able to absorb that fault and nobody would lose their power. So that gave us the first clue of how important this would be in a power system that have rapid change and stresses. Okay. Over to how to better coordinate. So use case #2, TSO, DSO coordinated operation. So this is a topic that is more and more on the topic in Europe now. So just imagine if we have this kind of probabilistic risk analysis tool model and installed at the TSO. And just imagine if you have the same one for the DSO. And if you just imagine that the risk for the flow between the system is coming from the one calculation to the other, then you can get the effect of, for example, the TSO's calculation and the flow going into the DSO and the additional risk with that flow. You can then get a common view of what's impacting the TSO and DSO based on the direction of the flow in or out of the models. So when the root cause is affecting both of them, the risk will increase both at the TSO and the DSO. They can pick up the phone and coordinate what action they can do to reduce the risk for the whole system. So this kind of coordination, instead of optimizing your system, don't care about your neighbor, you don't care about your neighbor, and that benefits all. And to a very important topic in Europe today and the rest of the world, large consumer of power that is in queue for getting access to the grid. This is an example for hydroaluminium in Norway, which consumes approximately 10% of Norway's total consumption. Same logic, if the large consumer of power have a model of the surrounding power system feeding their system, and the same goes for the TSO, and you are feeding the risk from the TSO system into their model, they will also see when the risk in the surrounding power system is high, affecting the large consumer of power's production. So by coordinating their operation here, they will, or they can, for example, in a high risk in the surrounding system, the TSO can ask the large consumer of power, you need to reduce your loading for the next half hour, 2 hours, what have you, to reduce the overall risk, ensuring your production. The same goes for data center. Their backup system could be put in operation in times of high risk in the surrounding power system, and in that way helping the grid owner instead of just being a consumer of power. Okay, over to the conclusion and summary. So how much can we utilize our power system more in a safe way? Maybe 30%. Going from today's N-1 criteria to quantifying the risk and allowing for higher utilization tomorrow. And having a high reliability on load delivery. And where they start is to start quantifying the security of supply in power system in real time, probabilistically. That's the only way we can achieve this kind of safe coordination. So everybody needs to work in perfect balance, where all participants play in perfect harmony for the system to work. But for all the TSOs, all the DSOs, all the large consumer of power, it has to work in perfect harmony to ensure that the risk is kept in acceptable levels at the same time as we utilize the system more. So the shared risk and the shared nodes for one harmonious system. So to summarize, probabilistic risk analysis give us a new insight, and in our mind is the key to better utilization. It allows for better coordination for future power system needs in a secure manner, and it opens for coordination of system operation, planning, investment, cross companies, cross nation in a new way. And it also laid the foundation for EU's new grid package and increased cross-border utilization safely, giving the power grid the time it needs to adapt for the coming decade. And there is a project going on in Norway, an R&D project called MaxGrid, where exactly this is has to go to being demonstrated. So I recommend people to check that out, where probabilistic risk analysis is central. So for my final slide, I just want to say thank you to RGE and the PCI Energy Days 2025. Thank you.
Thank you very much, Arne, for this wonderful presentation. I see applause on the screen. I hope that the technical part will work from now on. Luckily, it worked on your side. Maybe just in order to give people a bit of time to think about the questions that they have for you. I will try to take like 3 minutes to briefly introduce RGI again. Let me share my screen. And Arne, I hope you can maybe make a sign in case I get lost again.
Yeah, I'll let you know if you lose sound or something.
Exactly. Okay. I hope you can see my screen now.
Yes.
Perfect. Okay, let me go back to exactly. Okay, so just briefly for those of you who do not know RGI, we are a unique collaboration of NGOs and transmission system operators from across Europe. You can see on this map the regions and countries that we cover. It's most of the European countries, but of course we are looking forward to having even more organizations represented. And here you can see a bit how our work is structured. It is structured in 3 different dimensions because we are trying to have a holistic approach when looking at the energy system. This is why we divide our work into these 3 dimensions. One of them is grids and energy systems, where We enable discussions on how to model, plan, and implement decarbonized and optimized clean energy systems. The second one is energy and nature, and the name already says it, that we are focusing on ensuring how energy systems both onshore and offshore can be developed in coherence with nature and biodiversity. And the last but not least, we have our energy and society dimension, where we are looking at taking citizens on board, and as well as civil society and policymakers, and help develop strategies towards full decarbonization. This is who we are in a nutshell. Of course, you can always get back to us if you want to know more about any of the dimensions. But one important part of our work is also sharing best practices, which we do in the form of our RGI Grid Awards, which reached this year their 12th edition. We are offering an award in 3 different categories. Organizations can submit their best practices in technological innovation and system integration, in environmental protection, and in communication and engagement. And each year we offer 3 trophies in the 3 different dimensions to practices that are selected by our independent jury of experts. And all these practices have a home on our website, which is our database for good practices, and that you can visit on our website. They are all there. You can access them, you can read about them, you can get in contact with us or with the practices themselves. We just actually came back from Brussels. Arne mentioned it. Arne and Tørris won the award this year for the technological innovation and system integration category. And this is why in this webinar we wanted to go more in depth into this particular practice, and this is something that we do on a regular basis at RGI. We have a series of best practice webinars that happen twice a year, where we select practices that we think are highly relevant and very important to give them the opportunity to present the practice much more in depth. And the only thing that I still wanted to share with you, so this is the work that our technical dimension is doing, because Arne and Tørris practice won in the technical category of our awards. These are the work streams that our technical team is tackling with their work. In case you are interested in any of those, knowing more about them, please be in touch. But now, before I open the floor to your questions, I would just like to share the jury testimonial that was played on stage in Brussels on Tuesday, actually at the PCI Energy Days, where we had our award ceremony. And this shows you why the jury has chosen Arne's and Tørris' practice to be the winner in the technological category.
The jury is pleased to award this practice the 2025 prize for technological innovation, as it delivers exactly what Europe's power system needs now: an innovative and transparent tool for real-time prediction of grid risk that avoids reliance on proprietary black box platforms. By combining probabilistic forecasting with climate and weather data, it greatly improves situational awareness and risk-based decision-making across large customer loads and transmission networks. Tested with Norwegian grid operators, the solution strengthens coordination between system operators and major users and can be readily transferred and scaled across Europe. By safely unlocking at least 25% additional capacity, it helps accelerate the energy transition whilst reducing the need for costly new infrastructure. Congratulations to Arne and Tørris.
Yes, congratulations once again. And now I would like to open the floor for your questions. In the meantime, I think you had time to think about it. So please feel free to either unmute yourself and ask your questions directly, or you can also do that in the chat. I'll give everyone a bit of time to do so. Maybe I stopped the presentation so that we can see each other better. And now I see, Arne, that we do have some questions in the chat. So let me go and look at the first one. Okay, so I have the first question here from Hans Bering, who is saying Sunmore is an example that fires up the questions of the need of big few power lines modernization instead of a smaller, more spread out network.
Yes, and to try to kind of elaborate on the outage in Norway 2014. So the interesting takeaway for us at that time, so we were now learning the insight that the probabilistic tool could give. And we were lucky to have this on the Norwegian power system model. So you have basically many different regions. All regions have their different risk level or security of supply, if you will. And you have the total of Norway. So there were a lot of data to watch and look at. For the Møre case and the outage there, this was kind of what we learned there was that in this case, system operation evaluated that this situation they were in was okay. It should be an n-1, but there clearly wasn't. If the spinning reserve was in place, we would have an n-1. So it kind of showed us that in this kind of example, a situation occurred at a point, a Saturday or a Friday, something like that, and they did some small change. Let's reduce the production inside the area and import from the north is cheaper, which is fine. It's what you should do. But what you should also do is to have enough spinning reserve. This could be requiring flexibility now with battery package, what have you, for that next coming 24 hours. In that way, that action would be viable. So as we have learned by doing these analysis, first for scenario analysis of medium-sized network to large network, you get more humble for each analysis as you do, because all the different power system has their unique property that is changing by the hour. So to answer your question, yes, a more distributed system would be better in case of just having high flow on the top level and then transform down. But this is kind of the infrastructure we have, and now we have a very fast changing need of a power system that was designed for a different use. So yes, it was a unclear answer. Sorry.
Thank you very much, Arne. We have a next question from Robbie Morrison, who is actually one of the winners of an Outstanding Achievement Award last year within the RGI Grid Awards. He is representing the Open Energy Modeling Platform. So maybe, Robbie, you would like to unmute yourself and ask your question directly to Arne. It seems to maybe not be working. I heard some noises, but if not, I will just read the question to you, Arne. It says, Arne, initially you mentioned that the intellectual property belongs to its respective owners. Are there plans to open license the source code and data standards, assuming this is not currently the case?
Yes, I can try to answer this a bit vaguely. So of course, as an engineer in today's energy system, our power system is facing a huge challenge, and it's also our responsibility as engineers to step the challenge. And personal point of view, and for everybody else, it would be nice to just give this kind of knowledge to everybody, so it could be an open source for everything. But in our world, it's kind of, you need somebody to pay the salary for the people that has developed this. And the setup here, if we had enough resources, my personal opinion would be to give this to everybody for free. Just get this installed, implemented at everyone, so we can take Europe to the next level safely with regards to the power system. Unfortunately, it's IP for everything. But my point is here, the mathematics that is needed has been solved. Basically, if you have a number of years, everybody can do this. All the keys are there, but it takes a lot of time to do this development for the mathematical framework, putting this into programming code, testing it into real networks, verifying the result, doing this over several years. It's like a new medical vaccine, something like that, should be tested before it's open to market. And that's a huge amount of money that has been spent before that's the case. So I don't think I'm going to elaborate on that more, but my personal opinion, that's something I would like to do. And maybe down the road, I don't know. Let's see. I can't answer more on that one.
Thanks, Arne. Then we can go to the next question. It is a question from Nenad Keseric. I'm sorry if I mispronounce your name. Would you like to address the question directly, or should I read it out?
Yes, hello everyone. Maybe I can do that. Thank you, Arne. Very good presentation. Really interesting and amazing to see. Congratulations with the prize as well. Maybe you answered it partly now. I asked why does it take so long time for everyone to be convinced and implement, and basically it's the next question: how do we accelerate the use of these great tools into the industry? I mean, myself in the director role in Statnett, looking at this, so I know that's important, that's needed. How do we see the industry implementing it? And the second part was, how do you see this playing together with the different type of kind of DLR sensors and that are again being introduced in the network? So it's like to hear your opinion. Thank you.
Yes. Yeah, very good question, Leonard. And the first part of your question, it took me many years to understand this as well, because I couldn't figure out as an electrical engineer, when you're doing power system analysis, you're fascinated by the kind of the physics of the system, the inherent property of the system, and you get the result. You are used to that. We act on these results. And that was the case when we did scenario analysis many years ago, where we combined power flow analysis traditionally and risk and reliability analysis on the same cases. And so kind of the combined effect of, for example, a load increase on the west coast of Norway for electrifying the oil and gas installations offshore. And we saw how kind of this amount of increase of load will impact the whole areas, the whole west coast security of supply. So this should be the driving parameter for the decision making, what investment to do and not do. To our surprise, there wasn't any counter analysis being done, so that was a bit surprising. So this was like everybody's assessing their own way. Okay, then we can have a problem. And to understand why that was done, it's back to basically the design criteria of our power system. So that is basically a deterministic design criteria, n-1. And that criteria give us spare capacity to have a high security of supply in the system, high reliability in the system. And since that is in our backbones as electrical engineers, and when you're posing a new question, what about doing this probabilistically? This kind of a terminology that people are not used to, can't grasp it. So the last couple of years we are struggling with finding the kind of the right pitch to make it easier to understand. You could say that, let's say you never go to a casino and gamble, but if you're forced to go to the casino and gamble and put your asset on the table, don't you want to know your odds? Don't you? Would you like to know how to count the cards so you put the right bets? So it's kind of I think that is a kind of a conservative business that is not used to this kind of change. To the second part, how I see this being implemented, I think hadn't it been for the fast change in our energy system right now, this would take many, many years. But since now all the TSO, DSO, just the last 3 years are now forced into a situation where they have more challenges in system operation, but also planning of operation, and definitely on the investment part, because if you have a planned data center coming in 3 years, the market is changing and you're gonna make a decision on an investment that costs a lot of money and the data center is not coming anyway, you're exposed for wrong decisions. So I think just the size of the problem and realization for, I think, everybody that if this is a system problem we have on our world's largest machine, the backbone of Europe's society, we are forced to act, and that's what I think is happening right now. And I see also politicians also getting more and more involved in that. We need to utilize what we have more to give the system the time it needs to adapt. So even though we throw all the money on the world on the problem right now, it's still going to take many, many years before those investment is operational. In the meantime, we need Europe to to continue as they have planned. So the last part of your question, DLR sensors. So there's a slide I should have included. So DLRs, other smart grid technology, advanced system protection, battery banks, what have you, all of these tools will play an important role in the final solution. But what is missing is kind of how much of each, at what time, at what location, that is missing. And here the risk calculation comes in, because there you basically will see the effect. If we put 20% of DLR sensor in our system and we can utilize these power lines, 20% of them, let's say 15% more in this period, we can see the effect on how this will I'm losing my words, how it will influence the risk in the system. And then you can see it with and without, and you can calculate the difference, and then you have a cost incentive to do it. So I think it's super important for the investment analysis, should we invest DLR, what have you, you want to know with and without the impact on the security of supply now and in the future. That should be in your net present value calculation and evaluation. So I see the probabilistic risk analysis, if done correctly and implemented on a large scale, this will be a tool that will help CEOs, top management of TSO, DSO to do more cost efficient investment, the right one at the right time, right location. Should you maintain your power system? If you have a backlog on your maintenance, you're not able to maintain everything you want. At least maintain those components at those branches that will influence the security of supply the most for the whole system. So you know what you need to maintain. And also I think the most important part now, when the 70% capacity rule for the interconnectors are coming in full force this year, it's super important that TSO are kind of aware of the risk that is being introduced from the neighboring TSO and the other way around, so they can coordinate everything here. So yes, I think it was a long answer to your question, and thank you for the question.
Thank you.
Great. Thank you. Then we have another question in the chat. Actually, we still have quite a few. The interest seems to be high, so we're very happy about that. From Pascal Dietrich. Pascal, would you like to pose your question directly to Arne?
Yes, thank you. My question is, what is your take on the 70% min-ram rule? I think you just touched the topic just now. I was just wondering your assessment on your risk probability. Did that include already that rule? Or what would it change? Yeah.
Yes, so the 70% min-ram rule is just correct me if I'm wrong, but it is the remaining capacity for TSO and the interconnectors to have spare capacity. Is that correct?
Yes, that's correct.
Yeah, so it's kind of interesting, the 70% rule that is making 70% of the interconnectors available for the market. So basically basically forcing in certain instances a TSO to have a higher risk, basically. So, and there's not an easy or one answer to this, because in some situations, some interconnectors, you will have kind of the property in the surrounding system on both ends that there is kind of no problem. But in my mind, big interconnectors with high flow will, if you have a sudden outage on one of these with going, I don't know, 1,000, 2,000 megawatts, it's a huge stress on the system. So it's by itself, it's a kind of a risk to the system. But I think coming to, as long we can, if we always have our spare road to handle with an outage, you're fine, Zen -1, it's fine. But if you are going over the 50% threshold to parallel line, same capacity, you're basically, if you lose one, the other one won't cope. So you need to disconnect the amount that will trigger the other one as well. So that's kind of system protection, load shedding, what have you, that needs to be in operation. And again, the sheer complexity that we are introducing to our power system today by itself make this super difficult to manage for system operation. So flexing load, system protection, right amount of spinning reserve, producer, consumers, changing. So I think everybody needs to understand what is going on and when the risk is impacting different stakeholders, consumer of power or TSO, and between TSOs as well. So I think we saw in Norway and Sweden there was kind of a difficulties of I don't know, Statnet wouldn't allow for a certain amount of power more than they maybe should, and that affected Sweden. So this kind of political discussion is ongoing today. So I hope this kind of framework would be easier to get your counterpart to understand the challenge we have, since you are doing what you are doing to save your system or protect your system. Yes, again, sorry, a long question and an unclear question. There's answer, sorry for
Thank you.
Thank you, Pascal and Arne. So the next question in the chat is from Peter Crossley, who I see is on camera and might also want to address it directly to you, Arne.
Right, I'm Peter Crossley from the University of Manchester. My specialism is really power system protection and control, so the secondary systems. When we look to the past, a power system was very simple and was controlled really by humans, and our communication was analog using different routes. When we move to the future, all our communications, everything we do, will be dominated by Ethernet-based systems. All the control systems will be coming from Ethernet-based systems. So everything moves to a IP-based system. And those IP-based systems are really across all of Europe, across all of the world. So what happens when you have this very high impact, very low probability event, something that's never happened before, and the comms system stops working? Do we need a backup system that's there as a last ditch attempt? So I will tell you now, during the Olympics in London, every substation in the southeast of England was manned. Every transmission substation was manned so that you could phone an operator up. That has gone now. That's not possible. Everything is automatic. So is the problem the primary power system, or is the problem the secondary power system that's controlling it?
Yeah, very good question, Peter. And just to do a from where we came from with this master thesis from 2002, that actually was for trying to quantify the impact of the secondary protection and control system, the reliability of that one had on the power system. So that's where we started. So that's interesting kind of way into this, because at that time the different generation of protection and control have their different strengths and weaknesses. The old electromechanical had theirs, and then you got electronical and what have you. And where we are today, as you say, we are moving from our mechanical wired end-to-end communication and security of our system to kind of going into the cloud with everything. So to answer your question, so the most modern societies, the most digital society, are maybe the most vulnerable society as well. So let's imagine just a solar storm should hit the Western Europe like it did in the, when was it, 1850s-ish. What would happen to our power system then? So in terms of the primary component, maybe they would survive, but are kind of soft components with this digital transmission of data, what have you, will they get fried? And will then everything stop? So that is a good question. So I think to answer your question, I think we need to be very conscious of what we are doing in terms of how robust our system needs to be to tackle a low probability, high impact event. Because society will not will not survive very long without power in the system. And just in West of Europe, we do everything online, pay for food, what have you. If that doesn't work, we don't know what to do. And there is not many days if this is not fixed or having a clear plan. It's going to be a challenge for the future also. So I can't give you a good answer, but the robustness of the system is super important, and the backup system we need, and the spare parts we need to have. I think that's also a big hole that we need to cover. Of not only our secondary equipment, just the scale of a problem like a solar storm is maybe too big to handle, but at least if you lose some of your huge components due to something, how long time will it take before a new one is installed? I don't know, if a big North Sea cable is destroyed for some reason, how many months, how many years will it take to get it up and running again? So it's kind of these kind of issues that worries me as electrical engineer. The excitement for what we can do, but also the worry for how vulnerable we are. So yes, again, a bit of an unclear answer to your very good question, Peter.
Thank you, Arne. There is one more question in the chat from Hans Behring. He is not able to put his microphone on, so I will just read it out loud. He says, with this knowledge available, does it facilitate small producers on behalf? Respectively, does it set back huge investments in power stations and new huge grid 400 kV? Yeah, you can also read it.
Yeah. No, so what I would like to address in terms of investment. So I'm kind of a technological, not partying any kind of movement. I'm just looking at the power system holistically for the main task. What does it need to function as intended right now? So then if you change the production, increase the load, what have you, what needs to be done to keeping the lights on, basically. So for all the small production that's put into the system, done the right way, this is fantastic, but it has to be done coordinated. And the investment on the large infrastructure that needs to happen, because we cannot load the system in the pace we are doing without getting more road, more bridges, what have you, to transfer this. So we need to do all, small and large, all kinds of technology, but we need to do it in a coordinated way. And everybody can't have their own solution to a problem that is not well defined. So we need to agree on the problem and do the different solution in a coordinated way, and that the different solution is a hierarchy of how much they impact. So that's kind of missing in the discussion today, I think. Yes, we want to have a green power system, green production, what have you, and everybody's going to be electrified. Yes, agree on everything. But how are we going to do this in a coordinated way? I think here the probabilistic risk analysis will come into play in a way that will have a very high impact for decision making, reduce the political tensions between countries, making it easier for our politicians to understand the impact of the decision they are making today, and not being kind of not, how can I say this, not being fooled or having the wrong impression of this decision they are making now 10 years from now, because it's kind of if you do this tomorrow, this decision, it's going to have effect when it's coming in operation, and the society will ask, why did we put ourselves in this situation? Why didn't we know better? And I think until, let's say, a couple of years ago, you could get away with a lot of wrong investment in the power system, wrong decision, what have you. Nobody noticed. Now everybody is going to notice, because we are pressing it to its limits. And then we need to do this kind of safely, and we need to trade, or not, we need to communicate like a risk currency. So if my risk is impacting you, how can we cooperate for I help you now, you help me later, and a kind of this open dialogue. And then you need some kind of a parameter that is not in the system today. You can't do this on frequency, you can't do this on voltage to some extent, but you want to see this kind of total impact with the risk is the central topic, I think. Yes.
Right. Thank you so much, Arne. Exactly. That's what I actually wanted to say. I know that we have Alan Croes from TenneT. He is leading the energy system planning department at TenneT, and I wanted to ask whether he is able to intervene. But there he is with his question. Alan, can you unmute yourself? Yeah, it seems he can. Super.
Many thanks, Arne, for all the things that you've shown, and also elaborating indeed why it's difficult to introduce something new. And I definitely liked your parallel with the casino, which I think I'm going to use also to make it explicit. I think what you have shown us is also, let's say, indeed the steps that we can already take in a real-time operation, making sure that we're prepared and that knowing in advance, we can look at things and prevent, let's say, things happening that in hindsight we could have prevented. So I think you've shown the big steps that has been taken by you and your colleagues. There was, however, still one question in my mind, and I already put it on the chat, but also, let's say, try to figure out the next step, of course, of this probabilistic approach is, can we also use it to limit our investment or to do better investment? Because in the end, we're a high capex, let's say, kind of business, and customers need to pay for it. So with your approach, have you also already seen or examples that less investments were needed or better investments were needed, reducing kind of the tariffs for the customers?
Yes, great question, Alan. And this is where we came from back in we did the scenario analysis, and I think it's a super important question, because traditionally, when you're doing a power system investment or planning for something, you have kind of a future state that you want to plan your system for, and it's very costly. And we saw this in a case where we did, for electrifying the oil and gas installation from the main shore in Norway, we got this kind of discussion then. And then we saw that was very interesting, and how we came to the investment analysis use case for probabilistic approaches as well, based on the same thing. But by analyzing the impact a certain load increase will have or a change in a system, you want to test what power system upgrade will be the best one for your system. And if three are equal in how it will help the security of supply and solve the physical problem, one of these are cheaper, and that's the one you should choose. But also we saw that another case in Iceland, there was a new power line planned, and we got the information that, by the way, the spinning reserve in that area is changing from 70 megawatt to 120 megawatts. So be aware of that, of the sensitivity of your analysis. But just looking on the sheer amount of spinning reserve that was changing, that had a higher impact on keeping the security of supply than the new power line. So that kind of got us to the use case that by doing a lot of probabilistic analysis for future state and testing how your power system upgrade will impact the future security of supply and the connected cost that is you're trying to have as optimal as possible, you can then have a better, I think, foundation for deciding, can we postpone this power system investment, let's say for 3 years, 4 years, the amount of money we can save just to postpone it, or could we avoid it if possible? It gives us a much better resolution for doing our in-depth analysis and test it with a lot of scenarios and sensitivity for the net present value calculation for that investment decision. And we did this for, and I got good feedback from the Norwegian regulators, NVE, when we did a calculation on the impact of the Goliath platform in the north of Norway, electrifying from the main shore. And they said, by your detailed foundation of the calculation of the impact, I can't remember the amount, 50 megawatt on this point load in the system, and how it will impact the rest of the north part of Norway, it was very easy for us to give the okay to that application for electrifying it. So we saw then also in the communication with the regulators that as good foundation as possible for the future impact on cost. Cost is the driving factor that you have to understand, but that is connected to the risk and what will happen. Also give it a better way for TSO, DSO to really investigate the planned investment for the coming years. Because I think even though we had all the money in the world and we want to do everything now, it's still going to take a decade before that is up and running. So we need to utilize the system more, and being good in utilizing the system more, closer to its limit, and understanding what we're doing, we can utilize the system more. And to answer your question, yes, we can postpone investment for a couple of years or maybe longer. And the most important, not doing the wrong investment. We can't afford to do that. So, yes.
Thank you very much. And give it back to Maro.
Thank you. Thank you, Alan. Thank you, Arne. I think we are right on time to close the session at this moment in time. Thank you very much, Arne, for your in-depth presentation. It was a very, very interesting session. And as we see, the interest is high. There were many questions, many interactions. This is what our webinars are for. So I would say, just because also someone had asked in the beginning, we are going to have the recording as well as the presentation from Arne online. You can get in touch with us and also directly with Arne should you have follow-up questions. But we definitely want to see how this work is going to go forward, because it is indeed timely and interesting at the same time. And maybe we will organize a follow-up webinar to see how this work has progressed. But in the meantime, stay in touch with us and look out on our website for the upcoming best practice webinars as well. Thank you very much to everyone, and goodbye from our side. Thank you, Arne.
Thank you. Bye-bye.